Hello. In the past, a handful of individuals have referred to some of the Rust code I've written as exemplary or something similar, stating that they show it to others to learn how Rust code should look. I'll share some of the principles, practices, and patterns that I believe have led to this perception, and note that this is descriptive, not prescriptive. Idioms are what people make of them, and I don't expect everyone to agree with or adopt all of these. A number of them I've violated myself, and some of them I regret doing so on a number of occasions. Generally speaking, idiomatic code, if it's not idiomatic, it can be hard to read, maintain, and extend. And by following best practices, standard naming conventions, implementing proper testing, etc., the number of bugs and security vulnerabilities are reduced, particularly for code written in the future. Quality code also has the potential for better performance as you can leverage zero-cost abstractions, and the compiler is able to take advantage of known patterns to avoid unnecessary checks, among other things. Even if performance is not important to your use case, I sure hope that avoiding bugs and security vulnerabilities is. Fixing bugs is difficult and time-consuming, not to mention the potential for lost user trust, reputational damage, and legal liability if a security vulnerability is exploited. And all of this costs money, whether in time, lost customers, or legal fees. And finally, writing quality code reduces cognitive load, making it easier to focus on the problem at hand rather than the quirks of the code. You will be able to have developers, both new and old, focus on the problem rather than struggle to understand the code itself. To start off with project structure, I want to note that there are two ways to organize modules. Assuming you use the defaults, which you should absolutely do, your entry point to a crate is either lib.rs or main.rs, depending on whether you are a library or binary, respectively. From there, each submodule can either be a directory with a mod.rs file inside of it, or a file. If the module you're adding, like alpha here, has no submodules of its own, it should always be a standalone file, not nested. And that's not a technical restriction, but frankly I've never seen it, nor did I even consider it as a possibility until I was writing this. If it does have submodules, like beta, which has submodule gamma, then you can choose between having a beta.rs file, like on the left, on the right, alongside a beta directory, or having a beta directory with a mod.rs file inside of it. Aside from placement and name, the mod.rs file here is otherwise identical to beta, and depending on your editor, which I will touch on shortly, using mod.rs may not quite be as clear, and again, I will cover a workaround for that. Ultimately, there's no difference in functionality between these two approaches, and either is perfectly valid. My recommendation is primarily to just pick one and stick with it for consistency. Now, if you're writing code that abstracts over system APIs and want to have a common API, whether that be internally or externally, it's generally cleaner to have separate files for each platform to avoid cluttering the code with config attributes. Personally, I tend to use the config attribute on a module declaration to select the appropriate file for the platform while always calling the module the same thing. I can then re-export everything, as each OS should have the same API exposed. While not explicitly declared, if the attributes all fall through, then the module will load imp.rs, as the path is not specified, and that's just the default for module resolution. Not everyone likes this approach due to the use of the path attribute, so there is an alternative that's currently available on Nightly. That's the config select macro, which works similarly to a match statement. You specify the config the same way you would declare a match arm, and the relevant block is selected by the compiler. And once this macro is stabilized, I expect that to be the preferred way of handling this sort of situation. For larger projects, it's a near certainty that you will have multiple crates. When that happens, you should consider using a workspace to manage them. A workspace is a set of packages that share the same cargo.lock and output directory, making it easier to ensure dependencies and lints are kept in sync, as well as simplifying commands like cargo check that can be configured to operate on the entire workspace at once. And workspaces have other benefits as well, such as existing within a single repository, ensuring that code between sibling crates is always compatible, even if a rollback is necessary. Refactoring is also easier as Rust Analyzer is able to change code across multiple repositories in a single operation. And aside from cleaner code organization, Workspaces also allow faster compilation. Adding some more crates to the previous example to be more realistic, we can visualize the dependency graph. Both CLI and web depend on models, utils, and core, with models and utils also depending on core. But when looking at compilation, we actually want to compile core first, so we should reverse the arrows in order to visualize the compilation order. You'll note that the arrows from core and CLI, core to CLI and web skip over an intermediate crate, so we can get rid of them as there will always be something to compile in between. Now we can see how splitting one crate into multiple enables faster compilation. Core is compiled first, followed by models and utils. Note that these can be compiled in parallel since they don't depend on each other. After both of these are done, web and CLI can be compiled in parallel as well. The more crates there are, the more opportunities for parallelism exist, which is particularly beneficial on machines with many CPU cores. This doesn't only affect full builds, but also incremental builds. If you change something in core, everything needs to be recompiled, but if all you change is CLI, the compiler will recognize that core, model, and utils are all unchanged and only recompile CLI. Given in my experience, most work tends to happen at or near the top of the crate graph. This can lead to significant time savings. On to editor configuration, I highly recommend the Rust Analyzer extension, regardless of your choice of editor, as it provides countless features that make developing Rust code significantly more efficient. For example, it offers inline type hints, the ability to look up all implementations and even references of a type, viewing the expansion of macros, test debugging, and some features that I wanted went to file a feature request for, all before searching through settings and realizing that it already existed. Additionally, Rust Analyzer supports semantic token color customization, which is not easy to say fast. If you want mutable variables to be underlined, you can make them visually distinct. There are many configurations like this one, some of which are incredibly useful. I personally have the unsafe keyword marked differently to highlight its usage, along with all unsafe operations, which can be a lifesaver when working with and particularly when debugging unsafe code. I pulled up the complete list of what Rust Analyzer emits and includes 61 tags and 20 modifiers. Needless to say, you can do a crazy amount of customization with this if you have the time and inclination to do so. I use VS Code, which from various surveys seems to be the most popular editor. For VS Code specifically, I suggest adding something like the snippet on screen to your global settings. This will change the title of the tabs to ensure that files like cargo.toml in a workspace or your various mod.rs files are identifiable at first glance without needing to open them. And if you work on the Rust standard library or compiler, feel free to reach out for additional project-specific configurations that I have found useful. If you're not familiar with it, though, Clippy is a linter that is built into Cargo that provides hundreds of lints to catch common mistakes. It can be run with Cargo Clippy, and I can't recommend it strongly enough. Even if you don't configure anything, the default set of lints is great. As an example of the type of lints that Clippy provides, there is one to catch the example on screen. I've seen this written on 2 separate occasions in code reviews, wherein there is an arc of a mutex around a Boolean flag, and there's literally zero reason to do this. You're introducing reference counting, thread synchronization, locking, and the overhead of checking for a poisoned lock every single time you want to read or write the flag. Instead, you can use the atomic bool type, which handles all of this and is far more efficient. The arc mutex bool is 8 bytes, atomic bool is just 1. The atomic operation also likely optimizes to nothing more than a single CPU instruction, while the version I've encountered has non-trivial overhead. And while this isn't the most exciting example, it is a good illustration of the thoroughness of Clippy's lints, even for something as small as a Boolean flag. There are many more lints that catch potential performance pitfalls, as well as lints to catch common mistakes, stylistic issues, and even some security issues. If you haven't already, definitely give it a try. And in this admittedly contrived example, we're taking a slice of integers and computing the sum of the squares of the even numbers. In most programming languages, this is 100% how things would and should be written. In Rust, this will work, but there's a better way. By using iterators, we can express the same logic in a single expression. We turn the if statement into filter, the right-hand side of the assignment into map, and the for loop itself into a method call. At the end, we simply call sum to consume the iterator and produce the final result. No temporary variables needed. And it's worth noting that iterators are lazy, so all odd values do not exist as far as map is concerned. If we need to change the code, it's faster to see what's going on and to make the change without worrying about messing anything else up. In this specific example, the iterator version is more concise, easier to read, and generates better assembly, as the for loop has to do bounds checks that are not optimized away by the compiler. The iterator version does. But when dealing with operations that fail, there are a handful of options. One is to panic, but that's generally reserved for errors caused by the programmer, resulting in an unexpected situation that shouldn't need to be handled by other parts of code. For anticipated errors, such as a network request failing, a file not being found, for example, the idiomatic way to handle these is with the result type, which can represent either success or failure. However, it's important to note the difference between an operation failing and an operation not producing a value. As in this example, the database query completes successfully, but there is no row matching the query. So that's not a failure, that's a successful operation. It just found nothing. Given this, the option type should be used to indicate the potential absence of value, while result is wrapped around that to indicate the possibility of the query itself failing. Having a result of an option is not uncommon to see, to the extent that there is actually a transpose method on both types in order to switch the order if needed. Here's an example of what many newcomers to Rust attempt to do, mimicking patterns from other languages. There's a struct dog that contains an animal struct, essentially inheriting its behavior. This leads to very tight coupling of the two types, not to mention the difficulty of writing a method that accepts any kind of animal. After all, the only way to know what type of animal you have is to look at the dog struct, which doesn't exist as far as animals concerned. This inevitably leads to significant confusion, boilerplate, frustration, and unidiomatic code that's difficult to maintain. Instead, we get rid of the animal struct entirely. We keep dog around, as that's something we do want to represent. For animal, it's now a trait that describes behavior rather than implement it concretely. So long as the animal trait is in scope, we can call make noise on any type that implements it. And in this manner, traits serve similar purposes as interfaces in other languages, but with more flexibility and explicitness. If a function wants to accept an animal, it can do so either by monomorphization, which is when the compiler generates a specific version of the function for each type, or by accepting a din animal, wherein there's a small amount of runtime overhead for dynamic dispatch. Either way, the function can accept any type that implements the animal trait, rather than accepting an animal struct in managing dispatch by hand. Traits are used in essentially every Rust program, so understanding them is critical to writing idiomatic Rust code. And you can also use traits in a different way, adding a method to a pre-existing type, generally because the type is defined in another crate. In this example lifted from the time crate, we add a seconds method to i64, so the integer literals have seconds method that returns a duration. Extension traits can have any number of methods, though they're commonly used for only one or two. And to use the new method, the trait does have to be in scope. This is trivially done by just using the trait as an underscore, and this is done so that the trait does not pollute the namespace with its name, but it's still available for method resolution. And in this purely hypothetical example, we have a contractor using miles and the government using kilometers. Somewhere else in the code, two values get added together, resulting in the loss of hundreds of millions of dollars. How can we avoid this? Sure, we could be careful, but humans are pretty stupid. They're using miles after all. Instead, we can use the Newtype pattern to create small tuple structs that wrap the underlying value. And by defining the allowed operations, we can ensure that the compiler will prevent us from mixing up units. As a bonus, it will perform conversions when necessary, ensuring that our purely hypothetical satellite will not turn into fireworks for the native Martians. And just as with extension traits, you can add or even override methods on the Newtype by using an inherent impl. If a method of the same name exists on the inner type, the Newtype's method will take precedence. Next up is a relatively niche but useful pattern I have found for deserializing data that shares much in common but only has an additional field or two. To handle this, we can create a wrapper struct that includes the original type, which is the generic T here, along with the additional fields we want. By using the Cerity flatten attribute, Cerity effectively treats the fields as if they're part of a single struct, not nested. To be a bit more ergonomic, we can also implement deref and deref mute to allow easy access to the inner type's fields and methods. All we have to do now is use the wrapper struct where needed. When done correctly, this pattern can result in trivial boilerplate in a centralized location, while only requiring minimal changes to existing code to support the additional field. Here, just replacing the type of the parameter. Without this pattern, you would likely be stuck duplicating the entire struct or writing a custom deserializer, neither of which is particularly appealing. And here we have a pattern that probably isn't used as much as it should be, and is one of the patterns I regret not using in major crates. It's very common to see enums that are used directly in public APIs without much thought about the implications. Enums, by design, do not have private variants or fields. This means if you expose an enum in your public API, you're committing to have that representation for the lifetime of the API. By wrapping an enum in a struct, you can gain complete control over the public API. None of the implementation details are exposed unless you explicitly choose to do so, and as a result, you can remove no longer needed variants without breaking downstream code. Or you could even refactor the implementation details entirely. If you were considering having a number of types instead of an enum to begin with, this pattern allows you to expose only a single type, which simplifies the mental model for downstream users and makes it easier for them to handle. In the standard library, this is used for the IO error type, which is internally an enum. The standard library then exposes methods on the encompassing struct to allow users to determine the variant, though there is some additional categorization that happens to make things more logical on the user's end. This is a great example of where the pattern is used effectively, and where people likely don't even realize that it's being used. I've personally found this pattern to be incredibly useful, and not just for error handling, though that is certainly a common use case. If I'd followed this pattern in the past, I would have been able to simplify the public API of the time crate, eliminating factors that extremely few, if any, users care about. Instead of exposing 2 enums with 5 variants each, and having there be differences in the API depending on what feature flags are enabled, all of this could have been extracted away behind a single struct with no loss of functionality for users. And for the rare user that did need the full power of the current API, I could easily add methods to provide that power while still simplifying the common use case. Needless to say, next time I make a breaking change for this crate, moving to having an enum within a struct for this situation is a near certainty to happen. And another useful feature is the non-exhaustive attribute, which can be applied to structs, enums, and enum variants. And this attribute prevents pattern matching in other crates unless you include a catch-all arm for enums, or use the ... syntax when destructuring structs or enum variants. And that ... just shows that there are additional fields, essentially. Use it anytime you want to make, or might want the ability to add a field or variant in the future without it being a breaking change. That's pretty much all there is to say about this attribute. It really is that straightforward. Another common pattern is the builder pattern, which lets you construct large objects step by step. There are a few variations regarding the specifics, so I'll cover one of them here. Suppose you had a struct foo with two fields, alpha and beta. We then define a separate struct, foo builder, which has the same fields, but wrapped in an option to indicate that they may or may not be set. The builder struct has methods for setting each field, and those take self by value and return self to allow for method chaining. And finally, there's a build method that consumes the builder and constructs the final foo object. In this example, the build method would generally panic as a result of unset field, because that would be the fault of the programmer, but it could also return a result indicating success or failure. If any of the fields in foo are optional, the corresponding builder methods can be omitted, as is the case with beta here. The build method can provide default values for those objects, or for those fields rather, if they were not set. It can also perform additional validation to ensure that the constructed object meets certain criteria, or any other logic that needs to be applied before the object is used. And among the various design patterns being discussed, the builder pattern stands out as one that is likely to die off pretty soon, at least for most cases. That's because there's an upcoming feature, default field values, that will allow you to specify default values for a given field directly in the struct definition. What's on screen is the actual syntax that is proposed and implemented on Nightly. It's already been through the RFC process. Its implementation has been making good progress. With this feature, you can emit a field when constructing an instance of the struct, if and only if it has a default value in the definition. To indicate that this is the case, you can use the ... syntax, which is similar to the existing syntax for struct updates. This means that if you have a field or a struct with many fields, you can simply specify the ones you care about and let everything else fall back to the default value, as is the case for beta here. This is something that I thankfully don't see too often, but I have seen it more than once. An owned string implements the add trait for a borrowed string, so you can use the plus operator to concatenate them, which generally speaking is somewhat odd. This has some downsides, primarily that it moves the owned string, preventing its reuse and forcing any existing borrows to end. On the contrary, the format macro creates a new string without taking ownership of its inputs. You can also concatenate multiple strings in one go, regardless of whether they are owned or borrowed. The primary downside of this approach is that it is more efficient to reuse the pre-existing allocation of the already owned string, though unless this is in a hot path, the flexibility of format is typically worth it. If you do need to reuse an owned string, I would recommend using the push stir method instead, which has the exact same semantics as the add implementation while being clearer as to what you're doing. And to wrap up design patterns, I want to highlight the fact that idioms change. In the past, people would use the maplet crate to create a hash map with a macro, but once from iterator was added to the prelude, the general suggestion was to call hashmap from iter with an array of key value tuples instead. More recently, there was an unstable hashmap macro added to the standard library, bringing us back to what the maplet crate provided. Even further back to when I started using Rust, there used to be a try macro, and this is now deprecated in favor of the question mark operator that replaced it. The takeaway here is that while your code will remain clear as the language evolves, there may be a more idiomatic way in the future to express the same intent. This isn't a bad thing, though if you're refactoring code anyway, it's definitely something that you might want to keep in mind. For error handling, there's a number of ways to handle errors, but generally speaking, anyhow or error are good choices for binaries when you don't care about the specific error type, just that some error exists. This isn't recommended for libraries, since it forces your users to work with an opaque error type containing no useful information beyond the error message in a backtrace. Anyhow and error are very similar. Error provides a bit more functionality if you need it, but you're not going to go wrong with either. For libraries, this error is notable because it doesn't alter your public API in any way. It provides a derive macro to implement the error trait for your consumer error types, while at the same time generating code for display and from implementations. The main and realistically only downside here is that it will increase your compile times, but you're not likely to notice the difference unless your dependency tree doesn't already include sin and quote, which is quite likely. And finally, implementing from for your error types allows you to use the question mark operator to convert between them. This is especially useful because you're likely to call functions that return differing error types, and being able to convert them into a common error type with only a single character is a huge win for ergonomics. If you use this error, you can opt into this with a trivial attribute, and you should certainly take advantage of it. If you combine these approaches with other design patterns, such as using results when appropriate, and wrapping enums into structs, you'll find that error handling in Rust is not as painful as it may initially seem, and can be quite ergonomic with a little effort. And everyone's favorite thing to do, writing tests. While it may not be the most exciting topic, it's important to ensure that your code works as expected. In Rust, your unit tests typically go into the same file as the code they're testing, though it's not uncommon to have them in a sibling file. Integration tests, on the other hand, must be in a separate file and are located in the tests directory by default. One key difference is that integration tests can only access the public API of your crate, while unit tests can access private items as well. For this reason, try to write integration tests over everything, or to cover everything you can, as they shouldn't depend on implementation details and can survive even major refactorings. Other than this, unit and integration tests are largely the same as in other languages, so I won't dwell on them here. Property testing, though, is a great way to test edge cases automatically. You can write tests that ensure certain properties are always held true, regardless of input. As an example, you can accept a string to ensure that base 64 encoding it, followed by decoding it, returns the original string. The quick check crate makes this very easy to do, and it's quite configurable, even if you have some restrictions on your input. The best part is that if it finds a counterexample, it will try to reduce the input as much as possible to eliminate unnecessary complexity, and that can help you identify the root cause of the failure. If you have any unsafe code, property testing may not be enough. You should also run your code under Miri, which can catch undefined behavior such as out-of-bounds reads, dereferencing misaligned pointers, and even more. If Miri tells you that your code is exhibiting undefined behavior, that's not a maybe, it's definitely wrong, and you need to fix it. Something else you might want to track is code coverage, though it shouldn't be your only goal. The Cargo LLVM Cov tool makes it easy to generate coverage reports, and it can even be run in CI to ensure that your coverage doesn't decrease over time. Just remember, 100% coverage doesn't mean your code is perfect. It just means that every line, function, or whatever you're tracking has been executed at least once. You still need to ensure that the tests are meaningful and cover edge cases. Great. Now we can write code that's idiomatic, efficient, and correct. But how do you keep it that way? Maintenance is a big part of software development, and Rust is no exception. First up is simply keeping your dependencies up to date. There are numerous bots that can open PRs for this, and you can always use cargo update and cargo upgrade to do it manually. The difference here is update is some very compatible changes, while upgrade includes breaking changes that may require action on your end. For documentation, RustDoc is your friend. Rust's tooling is unmatched here. Take advantage of it. You can include examples in doc comments, and RustDoc will even run library examples as tests to make sure that they work as expected. Perhaps not as much for corporate code that only you are using, but changelogs are a critical part of communicating to your users what has changed in between versions. Anything is better than nothing here, though I've never seen anyone complain for having too much info in a changelog. And last for maintenance is CI. Basic checks like Clippy and Rust format are great to see, with tests being key for acceptance. If your tests take a while to run, consider splitting them into separate jobs or only running a critical subset, reserving the full test suite for releases. Without going into detail on these due to time constraints, here are some additional resources that can help you maintain a large Rust codebase and write idiomatic code. For license enforcement and security advisories, check out cargo deny, which can be configured to your needs and be run in CI. For checking semver compatibility, the cargo book has a chapter detailing many types of changes, whether they're major or minor changes, and the cargo semver checks tool can help automate checking weird edge cases that are easy to miss. To help with performance, Criterion is my go-to crate for benchmarking, while FlameGraph is amazing for visualizing where time is being spent in your code. The Rust API guidelines are a solid resource for naming conventions, interoperability, and more, and are closely followed by most crates. Finally, the Rustonomicon is a deep dive into unsafe Rust, and is a must-read if you are writing unsafe code or interfacing with C code. And that's what I have for today. Hopefully you found something useful to take away, and hopefully you'll be able to apply some of these ideas to your own Rust projects. I know it was a lot to take in, so just remember, if you have a few things and can apply them, that's a win in my book. The slides are online now. I'll be sharing the link shortly, so you can refer back to them at your own convenience. My username on most platforms, including GitHub and Mastodon, is JHPratt. Feel free to ask any questions you may have, whether it be on Mastodon, via email, or in just a moment. Thank you.